Somewhere in the fabric of space, right now, distances between galaxies are stretching. Every scientist agrees on that. What they can't agree on is how fast. Measure the expansion rate using the nearby universe and you get one number. Measure it using light from the dawn of time and you get another. Both methods are precise. Both have been checked, rechecked, and checked again by some of the best-funded, best-equipped teams in modern astronomy, and they refuse to match. This is the Hubble Tension, and in 2026, it stopped looking like a rounding error and started looking like a crack in the foundations of cosmology itself. Welcome to Astrion X. If this is your first time here, kindly hit subscribe for more science update. Today, we're diving into the disagreement tearing at the seams of the standard model of the universe, why the world's most precise measurements are making the problem worse instead of better, and the strange candidate solutions, from cosmic magnetism to a hidden cosmic void, that might explain it. Let's start with the number in question, the Hubble Constant, named after Edwin Hubble, who showed in 1929 that distant galaxies are receding from us, and that the further away they are, the faster they're moving. This simple observation was the first hard evidence that the universe is expanding, and the rate of that expansion is measured in kilometers per second per megaparsec. It tells you how much extra speed a galaxy picks up for every roughly 3 million light-years of distance between it and us. There are two fundamentally different ways to measure it. The first is the local, or late universe method. Astronomers use standard candles, objects with a known brightness, like Cepheid variable stars and Type 1a supernovae, to build a cosmic distance ladder, rung by rung, out into the nearby universe. Compare that distance to how fast those galaxies are moving away, and you get a Hubble constant of around 73 kilometers per second per megaparsec. The second method looks all the way back to the cosmic microwave background, the leftover glow from just 380,000 years after the Big Bang. By modeling how the universe evolved since then, using the standard cosmological model known as lambda CDM, scientists can predict what the expansion rate should be today. That number comes out at around 67.4. A gap of about 9% doesn't sound dramatic until you realize both figures come with tiny error bars. In early 2026, an international collaboration called the H0 Distance Network combined multiple independent local techniques, Cepheids, red giant branch stars, and Mira variables, observed across Hubble, James Webb Telescope, and Keck, to push the local measurement's uncertainty below 1%. Their result? 73.5, give or take less than a kilometer per second. That's a discrepancy so statistically significant that the odds of it being a fluke are now put at roughly 1 in a million. Then, just months later, the final data release from the Atacama Cosmology Telescope in Chile delivered the death blow to the idea that this might simply be a measurement mistake. ACT spent nearly 2 decades mapping the polarization of the cosmic microwave background from 5,000 meters up in the Chilean Andes, complementing the temperature maps taken by Europe's Planck satellite years earlier. When cosmologists compared the two independent CMB datasets, they matched almost perfectly, and both still disagreed with the local measurement. As Columbia cosmologist Colin Hill put it, agreement between ACT and Planck makes the Hubble discrepancy even more robust, not less. So if it isn't a measurement error, what is it? This is where things get genuinely strange, because fixing the tension means changing our model of the universe itself. And that's a much bigger deal than it sounds. One leading idea is that dark energy, the mysterious force accelerating the universe's expansion, hasn't been constant throughout cosmic history. If dark energy behaved differently in the earliest moments after the Big Bang, so-called early dark energy, it could have briefly sped up the universe's expansion before recombination, shrinking a cosmic ruler called the sound horizon. A smaller ruler early on would force scientists to recalculate a higher expansion rate today to make everything else fit, potentially closing the gap. It's a compelling patch, but critics argue it creates new problems elsewhere in the data, particularly with how galaxies have clustered over cosmic time. A second, more exotic proposal comes from Levon Pogosian at Simon Fraser University and his collaborators, published in Nature Astronomy in early 2026. Their idea? Primordial magnetic fields. Tiny magnetic fields that may have existed since the dawn of time could have subtly sped up recombination, the moment electrons and protons first combined into neutral atoms. Using detailed magnetohydrodynamic simulations, the team found that a magnetic field strength of around 5 to 10 microgauss gives a preference for a higher Hubble constant that fits the CMB data just as well as the standard model, and in some cases, better. If real, it would be a genuine 2-for-1, explaining both the Hubble tension and the ancient origin of the magnetic fields we see threading galaxies today. A third, altogether different idea doesn't touch the physics of the early universe at all. Instead, it asks whether the Milky Way sits inside an unusually empty region of space, a large-scale cosmic void. If we're located in a bubble with below-average matter density, the local expansion rate we measure would appear artificially faster than the universe's true average, without any new physics required. It's an elegant conservative fix, but recent large galaxy surveys have struggled to confirm a void deep or wide enough to fully explain the gap. What makes 2026 such a pivotal year is that these ideas are now being tested against each other with real data, not just against the standard model. The ACT team did exactly that. By comparing their high-resolution polarization maps against several of the leading extended models, they found that many of the historically popular fixes, ones that modify only the early universe without touching dark energy today, no longer fit the data well. As ACT cosmologist Erminia Calabrese described it, the new results have virtually removed the scope for many of these ideas, shrinking what she called cosmology's theoretical playground. That doesn't mean the mystery is solved, it means the field of suspects is narrowing, and whatever the true answer turns out to be, it will have to satisfy an increasingly demanding set of independent observations, from supernovae to the cosmic microwave background to the large-scale structure of galaxies. There's a broader question lurking underneath all of this. The standard cosmological model has been remarkably successful for over 2 decades, correctly predicting an enormous range of observations. If the Hubble tension is real new physics, rather than a subtle systematic error we haven't found yet, it would mean our elegant picture of the universe is missing something fundamental, an unknown ingredient in the cosmic recipe that has been hiding in plain sight since the Big Bang. Upcoming missions may finally break the deadlock. The European Space Agency's Euclid telescope and the Vera Rubin Observatory's decade-long survey will map galaxy clustering and supernovae in numbers large enough to put these models through exhaustive testing. Further down the line, gravitational wave observatories could offer a completely independent way to measure cosmic distances, sidestepping the standard candles and cosmic rulers that got us into this disagreement in the first place. For now, the honest answer is that nobody knows why the universe seems to be expanding at 2 different speeds, depending on how you look at it. What we do know is that the disagreement is real. It's getting sharper with better data rather than fading away, and somewhere in that gap between 67 and 73 might be sitting one of the biggest discoveries in modern physics. If you want to keep exploring stories like this, from the edge of known physics to the questions still keeping cosmologists up at night, subscribe to Astrion X, and let us know in the comments which explanation you think is most likely to win out.